Good evening, dear colleagues. It's a great pleasure to present you my work entitled The Dynamic Rupture of Interfaces Made of Heterogeneous Fracture Properties. So, what motivated us to study heterogeneous interfaces is some recent report and observation of very interesting phenomena occurring when a dynamic front interacts with a defect and heterogeneities. One of these work is the work of Xia and co-worker, who measure an increase in the apparent rupture energy needed to pull out some adhesive tape when they are made of heterogeneous adhesive properties. So here you have an example of a schematic of one of these thin film adhesive tapes. Another phenomenon that is observed, and really thanks David for giving a very complete introduction on transition to super shear, is that heterogeneities can help a crack to transition to super shear. So here it's a numerical work of Eric Denham, who studied the interaction of initially mode 2 straight crack with a tougher inclusion, and you see that this inclusion distorted the front, and when the front wants to get back to a straight position, you have here a focusing point where you get, which is a favorable site to trigger the super shear ruptures. And the last inspiring work from these French groups who studied the dynamic rupture of PMMA. So here you have just there the post-mortem view of the fracture plane, and you can see it's quite homogeneous, but as you increase the speed, you can see the apparition of these conic marks. So you have heterogeneous macro-scale rupture that are participating to the fracture process. And what is interesting is that here you have a graph and they measure here the density of this conic mark versus the crack speed. As the rupture increases, you have more and more of this heterogeneous conic on the fracture plane. But here you have to see that the crack is still a planar propagation. And once you increase the speed again, you reach another limit where you have these well-known dynamic instabilities, and you start to develop micro-branching. So the objective of our work is to understand a bit more the interplay between a dynamic crack front, planar crack front with heterogeneities. And to study this, we have a very simplified setup. So just to make the difference with the case that David presented you before, here it's a plane strain condition. So you have a crack that is straight and that will remain straight, and the stripes are here not as before in the direction the same direction that the propagation of the crack, but they are perpendicular to it. So a crack front has to break one asperity after the other. But so it's a plane strain bulk material, and I make stripes of alternately weaker and stronger asperity in order to keep a macroscopic fracture energy that is unchanged. So to solve this problem, I use a spectral boundary element method, which allows me to have numerical discretization only at the interface. And what I study is typically this. So I have two semi-infinite continua that are bundled together along the weak plane of propagation, and I have a plane strain condition, as I already told you. And the rupture plane is initially at rest under mode 2 loading, tau 0 here. And at time equal t0, I introduce a pre-crack on the left of my domain, and it will start to dynamically propagate on the right. And how I describe the fracture process is using a cohesive approach. So David also introduced this concept before. So it's also here a classical linear slip weakening law. And I have a constant average interface toughness, 90 Joule meter square. And then at the point I introduce some asperities. The macroscopic toughness is still the same, but you will see here two laws for the weak and stronger stripes with a toughness ratio that will be 5 in the case I will just show you now. So let's start with homogeneous rupture. So this is a space-time diagram. So here I have the position, here I have the time, and I am depicting the slip velocity. So you can see that on the left of the diagram I introduce the crack. Here you have an intact interface, so no slip velocity. On the left you have the broken interface when the slip at the interface exceeds the critical slip of my cohesive law. And here you have what is called the process zone, so it's basically the crack tip where the decohesion takes place. And you can measure the width of this cohesive zone by taking all the points that have a critical displacement, the displacement that is in between the critical displacement of the cohesive zone and the cohesive law and 0. So now you can see that this is the Rayleigh wave speed, so we have typically a crack that is propagating just at the speed under the small sub-Rayleigh speed. Now I will introduce some stripes of asperity here, but I will keep the macroscopic toughness constant. And as you can see, you have really a drastic change in the heterogeneous dynamic problem. So first of all, here you can trigger a sustained super shear propagation, even though the average fracture toughness is the same than before. And second effect, you have really high elastic radiation that are emitted at the interface. So if I zoom a little bit on this diagram, here you can see the stronger stripes, and the cracks accelerate when these stronger asperities are broken and generate pulses of velocity at the interface. And measuring the speed of this line, you can identify some elastic waves like Rayleigh waves and dilatational waves. So now our question is to understand what's the parameters that are controlling this effect. So I have three model parameters that can control the problem. I have the asperity size that can be compared to the process zone size of my cohesive law. I have some asperity toughness ratio, so the ratio between the strong and the weaker stripes. And finally, I have also the rupture speed. So here I have to mention that the last simulation I showed you, the speed were not constant, the track was continuously accelerating until Vitesse close to the speed close to the Rayleigh wave speed. But using this method, we are able to control, by playing with the loading, we are able to control the crack speed, and we can really do simulation where you have a constant crack speed all around the simulation. And what is really interesting is if you fix the crack speed of the crack, you have also a process zone size that is constant along your simulation. And what we did a lot of heterogeneous simulation at different crack speed, and we measure for each of them the width of the process zone size. And what you obtain is this. So here you have the crack speed normalized by the shear wave speed. Here you have the size of the process zone. So you start with a static value of the process zone size, and as you increase the speed, you have a contraction of the process zone size that is theoretically expected to be zero if the crack will reach the Rayleigh wave speed. And this has a link with what David explained to you before with this zero energy propagation if you reach the Rayleigh wave speed. So here the consequence of this is that you will have infinitely small process zone contraction. And I should really insist on this. So here I just show you the rest of the plot because I am in mode 2, so I can also generate the rest of the curve for super shear regime. But I have to precise you that this is not an artifact coming from the numerical model of cohesive zone. You can really observe it both analytically, so here it's a work of Huber and co-worker. You have to pay attention to the solid lines, where you can really predict it using LEFM development. So it's really similar to this. But also experimentally it has been observed. Here it's a recent paper of Svetlitsky and Feiberg on mode 2 rupture front, where they really measure as the crack speed increased this length of the contraction. So this is something that we are able to capture with this model because we only discretize the interface, so we have a very fine discretization of the process zone. So now I am able to fix the crack speed. So here on the left you can see one of the simulations where you have, here is half the shear wave speed, so it's a crack that has a constant propagation. And then I will introduce some asperity, and as I said before, you have this burst of slip velocity that are caused by the presence of asperity. And I want to quantify it, so I will measure the maximum slip velocity that is observed and compare the difference between the homogeneous situation and the heterogeneous one. And if I plot this indicator by playing with the asperity size, I obtain this graph. So I have really here the asperity size that is normalized by the width of the process zone size. And here I have the increase in the slip velocity. And I can really see that I have a sharp transition between two regimes of interaction. So if I have an asperity that is size that are very small, I have a weak interaction. And as I'm close to the length of the process zone, I have a really strong interaction, and I have an important increase on the slip velocity observed at the interfaces. So let's look a little bit at the interface to understand this phenomenon. So here it's still a space-time diagram, but instead of depicting the slip velocity, I just plot here the zone of the intact interfaces, then the process zone, and then the broken interface. And here, just to show the cohesive zone width will represent this. So I fix the time and I measure the cohesive zone width. So first case, you have asperity size that are in the range or higher than this cohesive zone width. And what you can see is that they are really interacting with the crack front. You can see that the crack front is really deviated by this, perturbed by this asperity, and you have successive acceleration and deceleration that are causing this elastic radiation. But now, if I decrease the asperity size and I choose a case when I am lower than the cohesive zone, the process zone size of my system, I can see that I have asperity that are homogenized inside the process zone because I have many weak and strong asperity. And if you look at the crack tip and both the slip, increase of slip velocity, you can see very negligible effects. So now we try to vary also the toughness ratio to see if we still observe the same phenomenon. And you can see that also here for different toughness ratio, this is really the length scale that controls the interaction with heterogeneities. And even if you have a very small toughness, so here you start from 1, which is the homogeneous case, and if we add a little bit of toughness ratio, you directly see also two regimes. So with the toughness, it's just a progressive increase of this, but this length scale is really controlling the phenomenon. For the rupture speed, so here I plot different rupture speed. It's also the same observation. What is important to note is that faster crack are less perturbed than slower crack, but it's relatively, because I normalize by the maximum slip velocity. And as you perhaps know, faster cracks also produce higher speed velocity. So in absolute, it will not be the case, but in relative, these cracks are less perturbed by the presence of heterogeneities. But something that is really important, and I go back to this contraction of the process zone, is that smaller crack will be affected by faster crack will be affected by smaller defects on the interface. Because you can see that this is normalized by the width of the process zone, but for all these three simulations, this size is not the same, because the faster crack will have a smaller process zone. So as my crack increases speed, it can see more finer details of my interfaces. So to conclude, using a plane strain setup where we were able to measure the effect of the interaction of a straight crack front with asperities, and we observed that we can have, even with a constant macroscopic, same macroscopic energy, toughness, we have a completely different behavior that can be observed. And one of the signature of one of this process is you have bursts of slip velocity that are observed at the interface. So then the question we ask is, since every material are made of heterogeneous, are composed of heterogeneities at different scales, what is the scale controlling if I have an homogeneous one and I can ignore these asperities, or if they are playing a role? And we observe that with this simulation that the scale that controls this phenomenon is the process zone size, and we can certify it by varying the toughness ratio as well as the crack speed. And finally, we also see that this process zone size is not constant with the velocity. It's shrinking as the crack speed moves toward the Rayleigh wave speed. And though that's explained why faster cracks are sensible to smaller microscale heterogeneities. And I put in the bracket more, because if you imagine you have a plane made of asperity of various size, and you have some kind of self-similar distribution, when your crack will accelerate, you will see more of these smaller defects of your interfaces. So that's it, and I'm happy to answer any questions.